Hey everyone, welcome to Foresight Space Group. And today we're lucky to have Dr. Ariel Ekblaw, and she'll be discussing her organization called the Aurelia Institute, as well as self-assembling space architecture. So with that being said, Ariel, please take it away.
Great. Hello, everybody. It's nice to meet this group. I had the pleasure of getting to know Foresight a little bit last fall when I met one of your founders, which was amazing. And my understanding is this is the space group in particular, right? Or is it also a bit of a broader group from Foresight?
No, this is the space group.
Great. Okay, fantastic. So self-selected space enthusiasts, thank you for your time. Great to be talking to the group. By way of a little bit of background on me, and then I'll get into slides and tell you more about the work that we do at Aurelia. I did my PhD at MIT in self-assembling space robotics. The idea being, how do we grow or self-assemble large-scale space structures far bigger than our biggest rocket payload fairings? Can we do it autonomously in a distributed manner, like a quasi-stochastic self-assembly without it being an agent-driven process with robotic arms or humans? And then after that PhD period, I ran a lab at MIT for 7 years. And then just recently, in the last 2 or 3 years, I have spun out a hybrid organization called Aurelia Institute that is a mix of a nonprofit where we are taking forward some of that MIT research, trying to do long-term horizon work for humanity's, expansion into the cosmos, thinking about space habitats. But then we also have a VC fund, a sister VC fund that can invest in stuff that we spin out, but also invest in best-in-class space deals and space companies that we see in the industry. So if you hear me talk about 3 organizations today, that's why. Started at MIT, then we have the nonprofit Aurelia Institute, and then we have the VC fund. So with that, I'll go ahead and share my screen and get into a little bit of the work. I am in a co-working space today, so if it gets loud and you guys are hearing too much background noise, just let me know and I can shift where I'm sitting and hopefully make it a little bit better. Okay, great. So space exploration. I'm sure this group is already very familiar with Artemis and the NASA plan to go back to the moon. I'm going to start with this today because we're just really excited that we had an opportunity to fly on Eclipse mission with that MIT lab. So,
hey, sorry to interrupt. We need people to mute themselves who have background.
Great. Thanks. So we started the MIT lab in 2016. This is the group that I ran. And we started by doing zero gravity flights. So I would bring students every year. I'd charter an entire zero-G flight. We'd bring 25 people in their research experiments. Then we started doing International Space Station missions. And then we started doing preparation for a lunar mission. And this is the tiny little Astro Ant, a robot that we just flew to the moon. I wish I had been on the Firefly lander. For anybody who followed the news closely, this one amazing week a couple of weeks ago where we had 2 landings on the moon for humanity in 1 week. We were on the Intuitive Machines lander, which did now famously for the second time flip over. So we were not able to get full solar power off of the lander, so we couldn't do our full mission. We're now looking for another opportunity to send this little robot to the moon. But this robot, Astro Ant, was inspired by science fiction, by Neil Stephenson's Seven Eves. The idea being, how can we have swarms of small robots live in symbiosis with spacecraft, really basically doing the inspection and repair and diagnostic servicing tasks that would enable spacecraft to be robust and resilient in the space environment, in orbit, maybe also on a planetary surface. And so we sent Astro Ant to the moon, and now we're excited to scale up that demo. So next scale.
Is it you who has background noise? Because I see everyone else is muted.
Let me see if I can move into a different corner. There is someone just across the room who's talking. Let me see if I can get a little bit further away from that. Sorry. Yeah, it might be. No, that's fine. It might be me. So besides the activity on the moon that we're really excited to be supporting, we are also thinking about what does it take to be able to do sustainable human life elsewhere. I'll say that the main focus of Aurelia Institute is doing space for Earth technologies. So we think about space habitat design, and we think about large-scale space infrastructures in low Earth orbit, mostly. But we are beginning to think about, because of the new push, of course, Moon to Mars with NASA and with SpaceX's plans for Mars, how we can support a future sustainable human Mars settlement. So we work a little bit on that work too. All right, so now by way of background, for the MIT lab, What we do is try to think about designing the human lived experience of space inside of the big structures. So we think about the products, the tools, the experiences that would make it a life worth living in orbit. We like to say that we're trying to train the space generation. So we bring researchers on these zero-G flights, which is actually something I think could be interesting to do along with Foresight. Try to get some fellowships together. If you guys, anybody has a project that requires microgravity, this is a really amazing way to kind of get going and get involved with our organization and also test an active project. Is everybody here familiar with the Vomit Comet? Yes? Has anybody flown in zero-G? Okay, well, maybe a nice opportunity to do a collaborative project of some sort. Basically, what the zero-G flight is, affectionately known as the Vomit Comet, it's a plane that does what you'd want a plane never to do. Basically pitches really steeply upwards at 45 degrees, noses over, and pitches really steeply downwards at 45 degrees. And at the top of that parabolic arc, you get 20 to 30 seconds to test out your research. And this is the baseline of how we do this testing. This is an example of some of the different research projects in our MIT portfolio. Everything from additive manufacturing, zero-G self-assembly, soft robotics, pneumatically actuated projects, anything that would uniquely leverage the environment of microgravity. We also do music and the arts. One of our most famous projects that we really enjoyed working on with a couple of musicians is how do you design a musical instrument that can only work in zero gravity? Something that's on the ground. So instead of importing cultural artifacts always from Earth, the kind of Earth orthodoxy of how we think, beginning to create new cultural artifacts uniquely for this amazing space domain. And this is our launch pipeline. So we start by bringing student projects on zero-G flights, then we get them onto New Shepard or a range now of suborbital opportunities. Then we bring projects that are of top merit to the International Space Station for recurring missions, sometimes 6 months or longer. And now, of course, we're excited to be also actively involved with the NASA CLIPS missions on the moon. The other thing that we do within this MIT lab is we think about analog environments. And so I lead missions with our team to the Arctic, to Svalbard, to be able to test some of our equipment in low light, low temperature conditions that are one of the closest analogs that we can get for lunar surface activity. So this is a mission that we did to Svalbard a few years ago. And if you're interested in learning more about the MIT piece of this puzzle, we have a book out with MIT Press. And the idea here is to mark the moment where humanity is going to have this really kind of profound expansion out into the near neighborhood of our solar system. And in the same way that we understand the Anthropocene as the era where humanity had a growing and ultimately dominant effect on our planet, we humans are soon going to have this really big effect in our cosmos. So the era of the Anthropocosmos is this dawning of this era where we, as our species, have a great opportunity, but also a big responsibility to think about how to be good stewards of the space commons. So we also do a little bit of policy work, and this is all reflected in the book. All right. So that's the preamble about the MIT lab and kind of the breadth of the research we do. Now I'm going to get into the particular project that was my PhD research and is now the main focus of Aurelia Institute. This is the self-assembly in space work. So if you look at all of the existing examples of actually inhabited space architecture, and then one prospective one up in the upper right corner is Gateway, you'll see that they're usually pressure cylinders, and they're often built in axial dimensions, XYZ coordinate system, so a Cartesian coordinate system, which always blows my mind because we're in space. We should be using radial coordinates. We should be growing in all dimensions, right? Like spherical dimensions, really making use of the space and the microgravity floating environment. So what would it take to change the paradigm of space architecture from this stuff to something like this, to a ring world? Again, from Seven Eves, if you can't tell, I'm very inspired by Neil Stephenson. What would it take to be able to scale humanity's ability to produce huge infrastructure in orbit? Well, one of the challenges is this is how the International Space Station was assembled, all of these different pieces and nodes and modules, and it was put together like this, by hand, in the way that humans have constructed things on Earth for millennia. but not really a scalable process. So as brave as this is, and as stunning and beautiful as of an image as this is an ESA astronaut trying to help assemble something that's going to attach to the Columbia module. And this is the gatekeeper to being able to actually scale and put more pieces of space infrastructure together, as we have to do it still by humans, working often with robotic arms. The way that I decided I wanted to approach this problem is more with inspiration from nature, from dynamic but directed self-assembly, where you can see, for example, in this spiral pattern, this phyllotaxis, there's a certain predictability of the base units. There's a code in the DNA that's saying, like, this is what the shape of each individual petal is going to be. And it allows a certain level of determinism, but also the energy of self-assembly that helps this plant form this ultimate megastructure. So inspired by self-assembly in nature from proteins and DNA and even larger scale flora and fauna, I have started this pathway now almost 9 years running to build and design self-assembling space structures that grow themselves in orbit. I'm going to play this video and show you guys a little bit about the concept behind this work. So the tiles, or the pieces that will ultimately form the in-space structure, we refer to them kind of lovingly as space Legos, they're going to be packed flat like IKEA furniture for their ride to orbit. But thank God, unlike IKEA furniture, you don't have to assemble it yourself. So you get to orbit, the rocket payload fairing opens, and then you'll see basically a glorified Pez dispenser. So these tiles are packed flat, and then they get released one by one. And the way that they're able to draw together, to be brought together, is with magnetism. So we're not using propulsion, and we're actually not even doing guidance, navigation, and control in a traditional sense. We're doing basically bang, bang hysteresis control right now to bring these tiles together with electropermanent magnets. So it's the opposite of an electromagnet. These magnets are always on, which is what's passively drawing the tiles together without requiring power. But then if the tiles don't bond correctly, in this artist's render video, you're seeing them all form perfectly into these buckyballs that are assembling. But in reality, if the tiles don't bond correctly, we can pulse current, we can pulse electricity through the magnets, through the EPMs, and dynamically correct and detach and try again. So that's the big picture concept. And then how do we actually do it? So we have now flown 4 generations, actually, of hardware to the International Space Station on zero-G flights, on suborbital launches with Blue. We also have a really elaborate physics simulation that has a layer of robotics control code on top of it so that we can study the dynamics of how a closed volume would self-assemble. We could be doing self-assembly of these pieces for any other number of applications. At the Institute, what we're really passionate about is this future for habitation. So we have to be able to show that in a reasonable amount of time, we can enclose a volume and ultimately pressurize it. So these are examples of a floret, a self-assembling subset of the TESSERAE tiles that were sent to the International Space Station in 2022. It's a photo taken by Michael Lopez Alegria on the AX-1 mission. We were really honored to be part of that historic mission. It was the first private mission to the International Space Station. And then this image that I showed at the beginning of the talk, now hopefully you can recognize in it the pentagons and the hexagons of a structure. We're working towards a habitat concept, building from these tiny tile prototypes that we've already deployed in orbit. We're building now towards human scale tiles, and ultimately a size of an inhabitable volume on the inside that's around 10 meters, maybe around 30 feet. And the rest of what Aurelia does is think about all of the inside components that would make it a life worth living. So we need to have vegetation, not just for health and nutrition and oxygen, but for good mental health. We should have musical instruments. We should have, a wealth and range, kind of the rich tapestry of what makes it an interesting life on Earth. We need to be also able to be thinking about it in a space context. Realistically, this habitat work is not trying to say that we think people are going to live steady state in this habitat in orbit, but more likely commute. And so for anybody on this call that has kids, I do think within your kid's lifetime, it will become much more common to have a job where you can commute to space for that work. So maybe they're a biotech scientist, they're trying to manufacture something in microgravity. Maybe they work for Hollywood and they're filming movies in space. But in the same way that now you can take a job that commutes to the Arctic or commutes to an oil rig, space and low Earth orbit is about to be able to be accessed with that type of regularity. And that's the type of habitat for a nearer future that we're trying to build. This is another example of some work that I'm going to show at TED in a couple of weeks. So I'm going to give a TED talk about the future of space habitats and what role they will play in society as we have this kind of expanding commercial activity in low Earth orbit. I'm sure many of you know that the International Space Station is about to be decommissioned. Elon apparently wants to accelerate that even more. And so we have a lot of interesting opportunity now for commercial players to take over International Space Station-like craft, companies like Axiom, Vast, doing really amazing work to be able to catch up and have these commercial space stations. We would like to be able to see the future of these space stations also have what I would say functional aesthetics. So NASA has been under so much pressure for so long to just keep the humans alive, which they do incredibly well in the International Space Station, that environment was much more primarily functional and engineering than it was about thriving. And that's because the astronauts that they're hosting at the top, 0.0001% of human talent, they can put up with that. But if we're going to design habitats to welcome a much broader range of occupants, we need them to be able to be more welcoming, like an enjoyable building that you would walk into on Earth. So we're also prototyping things like what you see in the bottom middle of this image, an algae stained glass window. Light would penetrate the algae, help produce oxygen for the habitat. So it's at least a partially functioning support for an ecosystem, an environmental control and life support system, but also designed in the shape of a rose window, because why not? Why not give ourselves a little freedom to put some beauty and delight back into space architecture? And ultimately, I think the reason that motivates me to work on space architecture is that we have this incredibly unique environment in orbit that allows us to do things we could never do on Earth. And that is incredibly tantalizing if we can get the funding and the logistics and the engineering credibility to go do that work. This is an image from the late 1800s of Newton's cenotaph that was promoted as an idea by Edward Boulay. They never built it. It was basically meant to be a monument to Newton. Those tiny, tiny little figures at the bottom of the big orb are people, just to give you a sense of scale. So it was over 150-meter span dome. But because of the forces due to compression and due to gravity, you're not going to be able to build a dome like this in the 1800s. It'd be a huge challenge even just to build something like this on Earth today. You could build something like this in the space environment. You have maybe the opposite challenge. You have to worry about pressurization and containment of forces, but we know that we have metals and alloys that can do that. And so we're now beginning to think about space as an opportunity to build things that we could never build on Earth, amazing monuments, something beyond just the purely pragmatic. And so this brings me to Aurelia Institute. So that was the work of my PhD, kind of now building forward on this main project around TESSERAE and habitats. We feel like we have hopefully begun the seeds of a real-life Starfleet Academy within our group at Aurelia. I think anybody who's a Trekkie here will remember Starfleet Academy was the place in Star Trek where the space cadets went to learn to become space doctors, space captains. It's also where the technology of the Enterprise was built. In modern life, the reality is we're one of many organizations that are part of a really cool, kind of Starfleet Academy network, but it's a dream of ours to be able to support that kind of activity. And so Aurelia is founded with this notion of being a humanist organization as we're trying to scale up access to life in space. Our main argument is that thanks to people like Elon and Jeff Bezos and NASA and ESA and ULA, the road to space is built. In just 15 years, the price to go to space has dropped from about $50,000 a kilogram in the NASA shuttle era to, with Starship, maybe $200 a kilogram. That's like FedEx. So if they can really pull that off, that means that the cost to get to space is so cheap that we can begin thinking about really instituting these broader dreams in a commercial ecosystem as well. We do 3 things at Aurelia. So we do space architecture R&D. I'm going to show you a little bit more of what we do beyond just the TESSERAE project. But we do fundamental research and development, and we have a big team of engineers and scientists and material scientists and designers. We also do education and outreach, which is where I'd also love to engage this community in that we bring 25 to 50 people every year on zero gravity flights, not just tourists, but to do real research, to test out anything that might be a mechanical system that would behave differently in a zero-G environment than in a typical gravity environment. And then we also do a little bit of policy. We try to think back to that notion of the anthropocosmos. How are we being good stewards of the space commons? How do I make sure that any debris from TESSERAE, for example, does not become space debris? Things like that. This is a diagram that kind of summarizes the technical development path that we're on right now for the TESSERAE project. So you guys saw the spacecraft tiles in miniature that have flown now multiple times to the International Space Station. We have a human scale, fully built, finished pavilion where we use it as a research platform to test out interior design for habitats. Then we're working on the engineering roadmap, the technology development roadmap, along with a really cool partner that we have, which I'll be able to talk about more in a few months, a company that we're going to be working with, a for-profit entity, to help us look at self-assembling at scale for the ultimate implication and implementation of a technology demonstration mission. And then ultimately the hope is to be able to, from having made one ball, one module, they can dock with berthing ports, something as straightforward as a CDM from the International Space Station, and ultimately have a multi-module space station. So this is an example of the habitat pavilion being constructed. It sadly does not self-assemble. We always make this joke that the whole, vision of the spacecraft version is that it's self-assembling, but on Earth we have gravity. We still have to have humans get up on ladders and self-assemble this modular baseline structure. And here are some examples of it fully built. We just did an exhibition at the Seattle Museum of Flight. So you can see it kind of across the Great Gallery Hall here. And then on the far right, you can see what the experience looks like on the inside. There's that prototype of the algae stained glass window, a zero-G kitchen, and we're really excited to be taking a lot of this work forward. Something else that we're working on, I'm almost done and I'm happy to answer questions. This is a very provocative design. The TESSERAE design was picked because a dome is very effective. It's a minimization function, right? It's basically we want to get as much volume as possible for the minimum amount of surface area because that's the expensive mass of stuff to put up into space. This is a kind of meant to be intentionally provocative space station design. We're doing it with Heather Wick Studio, a famous architecture studio and design firm out of London. And this is going to be exhibited at the Venice Architecture Biennale this summer. The idea being that this is uncrewed, no humans, autonomous plant growth experiments in each of these nodes, and they're intentionally separate. So if there's a blight or insects, each different little baby microclimate, can have different life support systems or different tweaks to the humidity and the temperatures of different environments, but also has that safety of compartmentalization. Does it need to look like this? No. Does it need to have really expensive, complicated telescoping shutters? No. But we are trying to, again, push forward with a different model of design for space structures and basically test the limits of what we think we could manufacture and realistically deploy. This is the artist's render. The actual spacecraft version will look a little bit different. We're doing a lot of the engineering, like aerospace engineering work in the background and the IDD work, and Heather Wick is doing a lot of the design. Just close with a couple other images of long-term work that we're excited about. Could we use self-assembly to help grow non-deterministic space stations? Things that can kind of accumulate organically module by module in the way that a city grows? Can we do beautiful integration of functional, safe rose windows in orbit? And then eventually, what we'd love to do is, partner with groups like VAST, who are becoming experts in artificial gravity, to say, how do we scale up what we can do with artificial gravity? I still think the right way to do it is not within a single module that's tiny, that spins, because you have to spin it pretty fast and you're going to make people get sick. It's to do it with a big diameter ring, so you can spin it slowly enough to still get close to 1G or a fraction of 1G. We could spin rings at the right rate to get 1/6 G and practice lunar gravity for years and years in orbit if we wanted to. Do the same for Mars as a way to prepare for ultimately, if we really do want to go forward with this, kind of SpaceX-led vision. And last thing I'll say, and then I'm happy to answer any questions, is that the background context for all of this very far future work at the Institute is that we have that sister VC fund. So if anybody's interested in founding a company or maybe knows some good space companies that we should talk to, we have invested in companies like Stoke and Turion, Think Orbital, a bunch of groups that are doing what I consider to be really fun, foundational, good technical work in the space industry to solve some of the commercial holes that we have to be able to make it a really viable space economy. So really delighted to talk with you all about any and all of this. And thank you so much for having me. I'm happy to answer a bunch of questions. Sorry again about the background noise. I hope it was clear enough.
All right. Well, thank you very much. That was a lot of information and very cool. I'm going to ask a couple of questions, which I actually, Lydia was kind enough to put in the chat, and then we can open it up for everybody. So, see, am I allowed to share, Lydia? Let me try.
You should be your co-host.
No, my share button is not enabled.
Oh.
Okay, I don't necessarily need to. So one thing is just a minor thing. I noticed that in some of your pictures, you showed multiple buckyballs kind of bonding on one of their edges, one of their faces. And just wanted to let you know, you may already know this, that if you, just like it's the 5-membered rings that allow it to get positive curvature, if you stick in 7-membered rings, you can give it negative curvature. And so you can make all sorts of structures with just the kind of joints that you have in the balls with, just the 3-way joints. You don't have to do these face-to-face things. Just a thing that you might want to look at, like fullerenes with negative curvature. If you search for that, you'll find these things.
Thank you.
And
we're
then
interested in buckyballs and truncated icosahedrons because they're plesiohedrons and they're space filling. But I will definitely look into the ring
let me see if
concept.
I can share it again. Let me just try again and see if I've gotten turned on.
It should work.
Share. Layouts enough.
Is it giving you like an error?
No, the share button, it shows me share screen, but the share button is disabled. Anyway, that's okay. Okay, next thing is, with your plants and that sort of distributed, modular, isolated sub-gardens, have you ever heard of the Millennial Project, which is kind of an obscure book that has inspired some of us at the Foresight?
I have not.
Yeah. Well, the Millennial
Tell me
Project,
more.
whose subtitle is called Colonizing the Galaxy in 8 Easy Steps.
Love it.
It's a very, very interesting masterpiece by this gentleman who published it like 25 years ago. I don't know what happened to him, but anyway, and it does actually go through a plan to colonize the whole galaxy, but starting with just the oceans of the Earth and then going to space habitats similar to what you described. But one of the technologies that he describes, because he's very concerned with like how to actually make this stuff sustainable, is, I don't know if you've ever seen these gardens you can get. I don't exactly know what they're called, but they're sealed glass globes, like complete glass spheres.
That have shrimp in them?
Yeah, they have shrimp and algae.
Yes. Yes.
For years and years and years. Somebody definitely has to put one of these in space, because these things can produce like spirulina algae, and they can start up whole food chains, and they basically require nothing except light to keep going, and maybe some hydrocarbon feedstock if you want to have them harvestable. Obviously, you need an input of mass. Anyway, so I would recommend, think about flying one of those, or maybe even building one of those out of your polyhedrous.
Love that. It's a big
challenge,
challenge, like biosphere level challenge, right? To
No,
be able
it's
to do it fully closed.
No, his point is that it's totally not a biosphere challenge.
It's just tiny little
Rather than
self-contained.
having every ecosystem on Earth and trying to manage a gazillion parameters, these things, we know they work. You just put them in a glass globe with 2 species and water, and they live for years and years and years with no manipulation, monkey business. Okay, so it's the opposite of biosphere, actually, and he makes that point. The other thing is,
Okay.
Yeah. Okay. The last thing is, okay, so now I have two more questions. One is how, and we're going to go from small to larger. So what I'm doing. So the magnetic self-assembly with those clever, whatever you call them,
Electropermanent magnets. Yeah.
electropermanent magnets. That's clever. So nonetheless, even given all that cleverness, with the realistic tip-off velocities and angular velocities that you might expect from your Pez dispenser,
Yep.
you simulated, and the masses of the objects and the control authority of the magnets, have you actually simulated that you can actually reassemble these things once they go drifting off in all directions?
Yes. So two things that we did. One, for my PhD, I had to prove that the assembly closed so that we could
Right.
solve the whole filling problem, all these problems with quasi-stochastic self-assembly. We
Great.
think we can do it under 8 hours in orbit, but that's based on a huge number of assumptions. We still have to calibrate the model and see if that's correct. We're doing our first deployment of all 32 tiles to form a full buckyball again on the International Space Station in January. So that'll give us our first chance to really
Right.
validate the model. And then the second thing is to keep all the tiles proximate, which you hit on the big challenge, because it's magnetism. So it, the strength dissipates with 1/r², actually 1/r⁴, depending on the geometries. We intend to contain the assembly in some type of a big
Like a
flexible
net.
membrane or a net, exactly.
Okay.
And that just keeps them close, and then we can retract the net when we're done.
Sounds great. Sounds like you thought about this stuff. That's obviously an important problem, and that's really cool. I'm glad to see that you didn't invoke flux pinning and all these exotic superconductors and stuff. You're just using plain old permanent magnets. That's brilliant.
Gotta
And
keep it cheap.
I presume that once these things are like initially aligned, then you can have other sorts of hermetic, and they've got to be airtight and all this kind of stuff too.
Yeah.
Right.
That's the biggest challenge actually for this system, is it's the beauty of self-assembly that makes it possible to build bigger than the rocket. But then as soon as we add in all of those seams, convincing NASA and other partners that we can safely pressurize it and with a small leak rate, even the ISS has a little bit of a leak rate. What we think we're going to do is one of two things. We'll either have to add gasketing to every bonding edge, and we'll have clamps, like train car coupling clamps, that come out at every seam. So once the magnets draw the exoskeleton together, the clamps cinch it all down together. What we could do on top of that, if we're going to have it extra redundancy for human occupancy, inflate a bladder on the inside and pressurize that bladder. And then those tiles are basically just an exoskeleton to the
bladder. Or seal it up with glue or whatever you need.
Yeah.
Fine. Okay. Next question. Last question from me for now. And this is sort of a question that comes up repeatedly in these seminars, especially when people are talking about large structures. And you're not the first, although you're certainly one of the more interesting ones.
Thank you.
Why? And what I mean by why is not so much, what I mean by why is this, as you know, with space enthusiasts, you often run into the situation when they're proposing space colonies or Mars bases or asteroid mining or solar power satellites or whatever. It's they're like, space is the answer. Now, what's the question? And so they just want to build big stuff in space or on other worlds, and then they want to leave kind of to the side how to justify this, other than just a visionary mission, a whole a quest for multiplanetary or it's almost for its own sake that people propose this stuff. And I believe that in order for this to be realistic and for people to actually put up the money to do serious megastructures wherever off the Earth, there's got to be an economic case that makes it self-sufficient, that doesn't cost $1 trillion like a Mars city what's going to cost. Okay. So what I'm wondering is, do you have any ideas for how this thing, I don't mean it has to be self-sufficient, never receive any inputs from Earth. I just mean it's got to eventually start paying it for itself at the multi-billion-dollar level and not the $1 trillion activation function. So how do you see,
how do we do that?
What are the things that people are going to, what are the investors going to get back, before we have a city on Mars or an O'Neill colony in space?
This is a fantastic question. I'm glad you asked this. This is basically what I'm going to talk about in my TED Talk in a couple of weeks, which is, it also tries to answer, why did everyday Earth citizens who aren't space enthusiasts, why should they care? So where is the economic value and what is the real benefit to human citizens value? We think we can do two things with it. And we're actually pitching right now to a bunch of really large scale philanthropists, but also banks. Like we're pitching Goldman and BlackRock because they see the value in it. So the two things are space-based solar power, not an application for habitats. We're going to talk about it. We can argue about it later. Space-based solar power. There's enough companies that are doing it that need help with the self-assembly in orbit to be able to reach thousands of solar panels. And then the second one is biotech. So I'm from Boston. We work with a bunch of biotech and pharma companies.
That's a for sure thing that if we're going to continue to engage in gain of function research, we should probably do it.
Put it off world. Yes.
Yeah, put it off
I
world.
would love to see it put off. But even before that, right, there's Takeda, Glaxo, Moderna. They all want to do protein folding for biologics.
But you know something? Look, okay, let me say something about that. And space-based solar power is almost in the same boat, although it's a different details. But people have been talking about growing proteins in space since the 70s and the Skylab. And
that's why we wouldn't have invested in it in the 70s. We let NASA do 30 years.
And they've made ovens for crystallization, and these things have gone up there. And there's never been a product, and there's never been a payback.
Because there was never scale. Because the ISS is built to do early stage benchtop research. I've done it myself multiple times. What we need is a large volume factory in orbit that can scale some of these things, like what Varda is trying to do. But we need to get Varda more real estate.
Yeah, fair enough. You need to show that you can actually grow something that's gonna make a profit.
Yes,
and you don't need.
I'll give you an example.
You don't need a large scale for that. You just need to show it once.
Sure. I'll give you an example of a company we just invested $2 million in, and the University of Michigan endowment, very conservative, huge institutional capital, just invested along with us. It's Lamb Division, amazing female founder, Nicole Wagner. She has already been able to produce in orbit artificial retinas. She's inserted them into mini pigs. They're on their path to basically doing FDA clinical trial. This artificial retina is really hard to do on Earth. It's 200 layers of a bacteria dopsin protein. We want microgravity for that manufacturing process because it's more pure. It produces a better retina. You know what insurance companies pay right now for a really far worse prosthetic is $200,000 per eye.
Well,
this is an example. If we could make enough of them, we could make money off of them.
That's a good example that I haven't heard before. And that's not protein crystals from the 70s. That's something new. That's very cool. Thanks for bringing it up. I look forward to seeing more stuff like that, like true biostructures rather than just crystals. Okay, fair enough. Yeah, all right. Well, look, I can keep.
Great questions. Thank you.
I'm
enjoying it. Thank you.
Does anyone else have a question? Let's see.
I also see some friends on the call. I just want to say hi, Angeliki. Hi, Mehek. Great to have you guys on the phone.
Lydia, do we want people to just speak up, or do we want them to post? And how's this going?
Either or, like whatever is best. I think Micah had a question though.
Creon already asked both of my questions. So.
Oh, okay.
Sorry.
Okay.
I can voice my question that I've already written in the chat.
Great.
Please.
Thanks for the talk, Ariel. Really interesting. So the magnetic self-assembly idea sounds really cool, at least. But I wonder what the benefit you get from that over just having like a together connected in a net. So they maybe have one edge already connected to the next with some small actuators that can
also do that.
Oh, you also do that? Okay.
We do that. Yeah. So that's like an origami stack. So we also do that.
Yeah.
The advantage to having, that is, I think it's a really good pathway. We're going to go down that pathway to try to build them with that origami hinged method. But what you lose with that is that if one of those, once you've formed a ball, say, if one of the tiles is damaged by a micrometeorite impact or has a leak, you can't just pop it off and replace it. The beauty of a truly decentralized system where all of the tiles are not interconnected is you can depressurize that structure, pop a tile off and pop a different tile back on. Hard to do that if they're all hinged. Then you have to have reversible hinges. That's a lot of potential mechanical failure points, gets a little bit more complicated. But I love that you brought that up because we definitely have dual pathways there for the two different approaches.
Yeah, cool.
Can you guys tell me where you're from, by the way? So like Matthew, where are you from? What do? You must love space. Like, tell me a little bit about yourself, and Creon too. Creon, I know of you, so hello. It's nice to meet you. But yeah, Matthew, what do you do?
But I'm based in the UK. I've just moved to Edinburgh in Scotland. Currently between positions, trying to figure out what my next thing is. But usually work in space weather, so trying to protect our space assets, satellites, and ground-based infrastructure from the worst that the sun can throw.
Hey, do you want to give us a talk on space weather at some point?
Yeah, I would love to. I have an item on my to-do list to send my title and abstract to Lydia. So TBC.
Excellent. Yeah,
I'm
that'll-
waiting for it.
Yeah. Yeah, in fact, that's a general thing to any of you. If any of you have a presentation you think would be of high interest to this group, we're always looking for interesting speakers. So contact Lydia. Okay, we got
Wow, we
hands
have
raised.
so many questions. Do
Is
you
it?
want to go first, Angad?
Yeah. Hi, Ariel. By the way, Louise Hamlin says hi. She's in London and she wanted to say thanks for the planning part. I just met up with her like last week.
Oh my gosh.
We were
Please
both
give her a
housemates.
hug.
We were both
Yes.
that is what it sounds like. So yeah.
Oh. And that beautiful house. I can't believe that beautiful old house burned down in Altadena, but say hi to her for me. Yeah, I hope she's doing well.
Yeah, she's good. So the question that I had was, you've been sort of like you started Aurelia as an FRO, right? And then
Yeah.
there's the VC thing. Are they connected or are they separate things? And what is the pitch like to the philanthropist? Is it that you're doing this research, but you're also finding ways to invest in companies? Is that the thing that appeals to the philanthropist?
Yeah. So it's two different things. I'll answer both questions. One, what is the structure? How are the two related? And then for the philanthropists, I think what we ask them to do is fund this vision of enabling not like space enthusiasts for the sake of space enthusiasts, space colonies, like what Creon was saying. We're asking them to enable a near-term future in low Earth orbit that can really benefit life on Earth. So we're basically saying space infrastructure for the benefit of Earth. That's what we ask the philanthropists to support. The way that the VC fund connects to the nonprofit, they don't own each other. They're separate legal entities, but the nonprofit gets some of the management fee and some of the carry from the VC fund. So that's a way to keep the nonprofit healthy and thriving over time. And the reason that it earns that economic benefit from the fund is that the VC fund gets to look and have right of first refusal on some of the cool tech that we're spinning out of the Institute. Stay tuned. We actually have one of our first spin outs that we'll be able to share more about soon that is an exact example of this model.
Okay, sounds good. Thanks.
Great. Katerina, I think you might have perhaps had your hand up.
Yes, I have a question. First, thank you so much for this amazing presentation and all these pictures. Really want to commute to one of the stations in the future. And I want to just thank you for all the activities, that you do within Aurelia Institute. My team, not me personally, but one person from my team actually participated in zero-G flight last year in Horizon program.
great.
Yeah,
Oh, I'm so
We
happy.
were able
Who
to-
was it?
it was Mati Palatic.
Oh, great. Oh, I'm so happy to hear that. Well, so now you can tell everyone that I really mean it when I say, if you want to fly in zero-G, come fly with us. We fly 25, 50 people a year. Oh, I'm so happy to hear that. I'm glad you
Yeah,
know someone who's
and my question is, sorry, I missed the beginning of your presentation, so maybe you already said it. I'm sorry.
Yes.
You mentioned the certification process that you want to certify your structures, with NASA,
Yep.
basically to be able to fly them to the space and then welcome people. Can you talk a little bit about this? What are the main challenges for you right now? Because I imagine that certifying the structures like that, especially being the human flight certified, this is like a big challenge. And what are you doing for this right now? Where you are with this right now? What are the NASA? How they reacting to that? What are the main challenges?
Yeah, great question. So I think we're probably going to be certified kind of like how inflatables are going through a certification process. So if you guys know MaxSpace, Aaron Kemmer's company, there's a couple different groups now that are trying to do this with birth tests and all these different ways to show that they are ready to be able to withhold the forced due to pressurization. We started with Marshall CAN. So getting basically a Space Act agreement and a CAN process with Marshall. They're doing a lot of this kind of like space habitat certification work. What we expect to do is start by, and it's expensive because it means we have to do a couple extra versions, but we're going to aim for an uncrewed but fully pressurized demo, which I also just think is the ethical thing to do. I don't want to put a human inside my space habitat until I'm really confident that I have proven to myself and to the team that it's safe. So we're basically going to build a full-scale demo in orbit, do that latching, do that pressurization, and then assess it, like have a bunch of sensors in it. And that, I think, will be a data set that really helps us get through the certification process with NASA so that they don't feel like they have to certify something that has never flown before and is going to have humans in it the first time. We're basically going to do an autonomous technology demonstration mission first. It means we need to raise a lot of money. So if you know people who would like to support this project, let me know. But great question about NASA certification.
Thank you. Thank you so much for this insight.
Timmy, hello.
Hello.
Hi. I
It's
haven't
so
seen you in
wonderful to
ages.
see you. Long time.
Just me too. Hi.
Yeah. So, okay. When I looked at your website for the VC stuff, I saw like 4 buckets of areas that you focus on. And
Yes.
for the space infrastructure one, the first thing that came to mind is that thinking infrastructurally typically entails understanding infrastructure not simply as a thing, right? But as a set of relations and processes and imaginations. Like when we talk about infrastructure, it's, you know, how you bring a variety of things together on the technical, social, and organizational part. So, you know, I'm a lawyer, and so law intervenes so that these concerns can be embedded in a particular environment of legal forms and relations. So given that background, you know, I'm listening to what you're saying, and I can't help, you know, the lawyer in me is like,
Yes.
okay, so the first thing that I think of is jurisdiction around the net, right? And
Yeah.
whether the individual components, one space object, seeing as they're designed to be kind of self-moving. And so if the net ends up failing, so then that jurisdiction breach is kind of not there as your safety net anymore. And say another system has some kind of magnetic potential to it, then there would need to be a coordination process, like at the ITU. If you want to,
Yep.
National Telecommunications Union, if you want to put a satellite up, you have to say, okay, let's make sure that both our radio frequencies don't interfere. So in
Yes.
my head, I'm thinking, you know, you come up with this idea of magnets, but someone else could have a magnet. And so you would have to coordinate, like, to make sure that your magnets, you know, either don't like kill each other or something.
attract.
Yes,
Yeah.
exactly. That's just some of my thoughts.
Yeah, these are great thoughts. So one of the things that we're trying to do is, right, because the FAA now requires it after 2018, you have to be able to have a credible deorbit plan to be allowed to get the launch approval to go forward. So we think we are going to have to prove that all of the tiles individually could deorbit and burn up on reentry. And it makes sense because they're a lot bigger than CubeSats. So if you can show that a CubeSat is able to do that, which now you also are supposed to be able to do, we should be able to show that for the tiles. What we might have to do is if a space object of ours, so say one of the tiles does get loose, and we should be operating in an relatively empty orbit so that we don't have anybody else near us that would be at risk of attaching to our magnets. But say one does go away, we can pulse current through the magnet to neutralize it. And so if we needed to do something like a deconfliction maneuver, we do have the ability to do that. Like we have some control over the system. It's solar powered, and each tile will have solar power. And this is one of the requirements that we'd have to have it be somewhat autonomous so that it can independently handle a maneuver like this if there's like an off nominal situation. For now, a lot of space hardware is aluminum. So there's not like a whole lot of ferromagnetic material up there, but still we have to, exactly as you're saying, we have to be able to think through these scenarios. I do think we need to get a little more sophisticated with space law and have a more sophisticated registry of objects than just what UN COPLIS does now. And then, you know, JSPOC and NORAD on the military side doing all of their debris tracking. But I think you raised a really great point to me. Maybe you and I should talk about it offline too, to think about what would be a useful, hopefully not overly regulated, but like a useful structure that we could even pioneer and agree that we would hold ourselves to be a good case study for a more complicated
And I
registry.
know other people have questions, but you know, there's this different big distinction between law as regulation, limitation, and law as a tool to enable an outcome.
Yes.
Right.
Yes.
So
And I
like,
think
you know, people don't
it's
want
a bit
lawyers in
rich.
the room because they're going to stop our project and say it's illegal. But, you know, law is also an infrastructure that can be used as an enabling function. Thank you.
And for, you know, future investors in a business that we might want to do around something like this for self-assembly, law is important because it gives for-profit companies the guardrails that they know they can safely operate within, which allows them to have the certainty that they can go out and operate without inducing a bunch of problems down the road. So I completely agree with you. Law is a great thing to be bound by. It's actually really helpful for companies to know what the guardrails are of good norms of behavior. So awesome. Timmy, lovely to reconnect with you. It's been too long. Let's do it.
Yes.
Let's connect after this.
I think we have time for one more question. So Sana, would you like to go?
Yes. Hello. Just because you mentioned some people give intros, let me do a quick intro. I'm an undergrad student at the University of Toronto. I study physics and math, and I'm actually a Zenith Fellow. So there's a few
Oh, great.
people, yeah, that
We've flown a bunch of Zenith fellows. Yeah. That's
yeah,
great.
yeah. And I'm interested in biotech. I've actually done self-assembly, but for DNA origami, so on the nanoscale. So I think
Wow,
this is
very
cool. It's like the big scale of it. Something I wanted to ask was, I know there are some, for example, Zenith fellows that you worked with, but I was wondering in general, for people who want to work with you or go on parabolic flights, what does that look like?
Mhm.
Also, I'm part of a lab, like Alan Gusposi's lab at UFT. He does more like material science, but he's pretty good. He's gotten like $200 million in funding last year from like Acceleration Consortium. And then he mentioned he wanted to do microgravity experiments as well. I was wondering, like, oh, if other labs want to work with you too, how would that work? I guess, like both sides of things.
Yeah, for sure. So for a student like yourself, we fly you for free because the whole goal is to be able to give people an opportunity without having to have raised money or get money out of their labs. So the way that you would apply is just to write to hello@aureliainstitute.org. We do generally go through the fellowship pathway. So we'll have like a Zenith flyer every year. We'll have a Brooke Owens flyer every year. But we always have a handful, like 4 or 5 people who just came to us organically, had a really good project, were credible. We make you go through a PDR-CDR process. So if you're familiar with that process from NASA, we try to make sure that the students were like kind of regardless of what their age and their prior walk of life is, go through a really good structured process so that your project is likely to succeed. But just write to me at hello@Aurelia. And then for the lab, we do also work with academic labs. At that level, we ask them to donate to the nonprofit a little bit, especially if your advisor has resources. But then we're super happy to basically be their Sherpa and help them through kind of their first experience in microgravity. And then we can help them also translate results from a microgravity flight to applying for NASA funding or applying for other opportunities that would give them a slot on the International Space Station, which is usually what PIs want, because the zero-G flights, as cool as they are, you really want long-duration micro-G to do proper academic research. So,
okay, yeah, sounds good. Thank you.
My pleasure. Thank you guys so much. This is a really great community. I'm really delighted to have been introduced to the Foresight Network. Thank you for great questions, and I'd love to stay in touch with everybody. Thank you, Lydia, for hosting.
Wonderful. Thank you so much. I do have one last question.
Oh, please.
In the next 5 years, do you foresee any like specific challenges or opportunities with regards to what you're doing?
Oh God, so many challenges and opportunities. Yes. So I think huge opportunity is the cost to get to space is going down so low that it's becoming close to what I would call democratized, and that many more people can begin to start space businesses that are credible, like the barrier to entry is coming down. A big challenge, one for the industry and one for human spaceflight. Challenge for the industry is whether we have a really robust launch ecosystem. SpaceX is amazing. They do have a little bit of an effective monopoly right now. Will we see Firefly and Rocket Lab and Relativity and Stoke provide and Blue, and Blue basically provide a more sustainable road to space ecosystem? And then the challenge on the human spaceflight side is we still haven't figured out radiation. So while we
can handle radiation, you just have to do some shielding, and you can shield with water, you can shield with food,
You shield with water walls. It's a great NASA proposal. It's true. But for like a mission to Mars, we're probably going to have to live underground. We still need to think about radiation. So I think it's still a bit of a challenge for fragile human biology. But maybe Creon, you and I should talk about space-based solar power and radiation after this. It's really nice to.
We could, that actually is an interesting point, Lydia. I mean, I know there's been endless numbers of these, but we could still do another one. We could have a space-based solar power kind of debate or discussion. I
love that.
Angelique,
I know which side I'm on.
That, and we could probably get some, like, I'm sure Angelique knows like the top people in this field, and we could get them and we could grill them. It would be good to have a space-based solar power presentation, if not whole discussion on this channel, because it's a thing that keeps coming up, and I don't know that we've done anything. Well, no, we had one. Maybe we even had Angelique. We had someone talking about a big project, but just the more general.
Yeah. Count me in for that one. I'll come back.
There's a lot of positive responses and thumbs up. So yeah, let's talk about it.
Okay, cool.
Well,
all right, we're at the hour.
We're at the hour. So thank you, everyone. Thank you, Ariel, and see you next month.